everyone. Good morning, everyone. I'm very excited to be here to present our recent work, which entitled is Dysarthric Speech Recognition System with Lifelong Learning Technique in Taiwanese Mandarin. I am Alim Misbullah from Informatics Department, Universitas Kuala, and I also work as engineering consultant at the APrevent medical company in Taiwan. And in this research, we work together with Jimmy and Mark. Sorry, I cannot pronounce the Mandarin name of them. So we are working to create an app called as the AI Speak. This app can be used by the people who suffer with the dysarthria and to make them can communicate normally with the normal people. So today, I would like to describe and explain what is the behind the AI Speak in terms of the machine learning approach. And to guide our discussion today, this is the outline. Start with the research background, and then the methodology, experimental setup, result and discussion, and finally end up with the conclusion. So all of you would like to know about what is dysarthria. So dysarthria is kind of the speech disorder that make it hard for the people to speak too clearly like the normal people. And this kind of the disorder can happen when nervous or the muscle or brain area that controls speech or image. So it can be caused by the several conditions like stroke, brain injury, Parkinson, or multiple sclerosis and cerebral palsy. But here in our experiment, we focus on the cerebral palsy disorder who suffer for the people in Taiwan. And people with the dysarthria may have the slurred speech, trouble controlling the volume or pitch. Sometimes their speech will be louder and sometimes will be too slow and may sound monotonous, and will be difficult for the normal people to understand what they say. And as we can see in recent years, by growing rapidly of the AI, the technology of the speech recognition already implemented in many areas and in many applications, and also the TTS there, right? So by taking this kind of the two technology, we are trying to finding the solution for the dysarthria people, and we try to develop and evaluate a dysarthric speech recognition, or we call it a DSR system, that accurately recognize speech from individual with cerebral palsy and varying level of dysarthria. To make our model that can be used directly in the application, of course, we have to collecting the data from the several people that suffer by this kind of dysarthria. So here we show the data composition that we already collected from the several hospitals in Taiwan. And the data composition consists of the two types of the data. The first one is dysarthria speak data set. This kind of data set consists of 74 speakers, which is the CBA, CB, and ALS. This is kind of the type of dysarthria. And the total number of the hours for this data set is about 150 hours. And while recording the data set, we use home environment, and we also use the portable devices like the iPhones. And all of the speakers are the Taiwanese Mandarin speaker who diagnosis as having mild, moderate, and severe. So it have the several level of the dysarthria level here. And the second data set that we are using here is the Mozilla Common Voice database. I think everyone who were working with the speech recognition already know about this data set, because this kind of data set can be really available on their website, Mozilla website. And for our experiment, we just chose the Chinese Taiwan data set to conduct the experiment. And besides this kind of two data set, we also recorded another data set we call as the personal DSR data set. And this kind of data set only focus on the 9 male CP speaker, because in our experience we just focus on the cerebral palsy speaker, so we just taking the 9 male speaker and collecting the data from them. We have the several dysarthria level 1 mild, 2 moderate, and 6 severe, and we record this data for the 4-time repetitions. And while recording the data, we use the 300 daily use sentences for the Mandarin language, and 3 repetition of the data we'll use for the training, and 1 repetition we will use for the testing. So to standardize the data, we convert all of the data set into the 16 kHz sampling rate with the 16-bit resolution and use the mono channel. So talk about the methodology here. First, we have to initial speech recognition model structure. Here in our experiment, we use 3 types of the approach to design our model structure. The first one is we use the factorized time delay neural network. It has been widely used in the speech recognition because it can capture long-term dependency with reduced parameter. The point here is the reduced parameter make it effective for the sequential data application like the speech recognition. And the second, we also stack the self-attention layer. This kind of the layer can assign the attention weight to input element and enhance the acoustic feature extraction and language modeling in ASR by selectively focus on essential part of the speech signal. And the third one is the spec augmentation. This also kind of the layer in the neural network that we can stacking in our structure. And this kind of spec augmentation will be generate more data set, more training data on the fly. We don't need to prepare the data set in the beginning by do the spec augmentation, something like that. But here we just put the layer, and this layer can augment it by itself with the spectrogram transformation. This is the idea behind the neural network. And we also use the lifelong learning techniques. If we talk about the lifelong learning technique, we already know that there are the technique that we are widely used. First is the transfer learning. If we talk about transfer learning, as we know that if we want to do transfer learning, we will use the pre-trained model, and then taking the weight from the pre-trained model to train the another model for the limited data set. And for the lifelong learning, here is the purpose is the continuously adapt and update ASR model to handle dynamic speech data involving speaking style, vocabulary, and context. So by using the lifelong learning, our goal is to ensure ASR system remain robust and adapt to the new linguistic and acoustic pattern. So with the lifelong learning, for example, if we train the model today and we have the new data for the tomorrow, and we will use previous model and to train the new model for the coming days. This is the idea behind the lifelong learning. And we also incorporate with the data augmentation. The purpose is to expand our data set and improve the model performance. To create the data augmentation, here we use one of the technique, we call it as a voice conversion for dysarthria. As if you remember that in the previous slide I mentioned, we use the Mozilla data set, and this Mozilla data set is kind of the normal data set. And when we use this kind of normal data set, we do the voice conversion to convert normal data set into the dysarthria data set. Converting the normal speech to dysarthria speech, and the normal speak will speak like the dysarthria speaker. So to perform this kind of the technique, we use one of the toolkit, we call it a crank toolkit. This kind of the toolkit can be trained the model to convert the normal speech into the target speaker in dysarthria speaker. So to set up the experiment, we first train the initial DSR model. In the initial DSR state, we train the initial DSR model. When we train the initial DSR model, we use the 74 speaker that I mentioned in the previous slide, dysarthria data set, and we create the general model. We call it as the general model. And the objective by creating this general model is to establish the optimal DS model for the baseline. This one will use for the baseline, and we will compare this kind of the model with the Google Speech API as a normal ASR model to see how robust our model later after we train using the Dysarthric dataset. So to conduct this kind of the initial DSR model, we use the model setup like here. To train the model, we use the Kaldi toolkit. This kind of the toolkit widely used for the automatic speech recognition. And to train the model, we use the MFCC feature with the speaker adaptive training for the GMM model. And we do force alignment to labeling the class for each speech in the audio. And we also perform the data augmentation. And while we train the acoustic model, we use the structure that we already mentioned in the previous slide, and then we stacking the convolutional layer, and also we use the additional technique like the spec augment to get the more robust result. And you can see from this figure, this is the structure of our neural network. You can take a look from the bottom until the up. As you can see from the bottom, we have the MFCC feature in the right side, 40 dimension, and then we're stacking with the spec augmentation layer. After spec augment, we incorporate with the convolutional layer, three kind of the convolutional layer here. And then after we take the three of the convolutional layer, we flatten with the TDNNF layer. At the end, before the output, we put the one single layer here. We call it as attention layer. This kind of the layer, like I mentioned in the previous, this layer we will use as the attention layer to learn more information from the network structure. And the second stage is the personal DSR stage. What will happen here is after we have the initial DSR model, and we will use this DSR model to train the lifelong learning. So for each speaker later, we will use initial model and personalize this model for each speaker that need this kind of the Dysarthric model. And for this personal DSR state, we divided this one into two states. First is without lifelong learning. The objective here is to simulate personal DSR performance over 15 days. So the simulation only performed the 15 days because we only have the 300 sentence recording from the night speaker there. And the second is with lifelong learning and incorporate with the synthesized speech state. So synthesized speech state is the kind of the data we convert from the normal speaker into Dysarthric, and then we combine together to create another model. And from this kind of the experimental setup, we would like to see when we combine the data with the synthesized, does it can improve the model performance or not. So this is the design of the lifelong learning. As you can see from the training phase, from the day one, for example, we already have the data that recording from the 74 speaker, and we train the initial DSR model. And also in the day one, we recorded the data from the speaker. And this kind of the data, we provide the transcription for them, and then they read the data, and we take the audio of the data, we put it together when we want to train the model on the day two. We call it as the PDSR. PDSR means the personalized DSR. So the initial model from the day one, we use it as a transfer learning from the day two until day 15. So in the day 15, we hope that by design this kind of the simulation, we hope that in the day 15, this kind of speaker, for example, Dysarthric speaker here, the model can recognize almost all of the sentence that speak by the Dysarthric speaker. This is what we hope when we design this kind of the lifelong learning state. And for the decoding, we use the testing data, one of the repetition from the recording from night speaker there. So this is the result for the first take result. In the first take result, we compare the decoding result from the normal ASR with the DSR for CP. The left column, the first column is the level of the speaker, consists of the 9 speakers there. As you can see, when we compare the normal ASR model from the Google Speech API with our model can work well compared to the normal Google Speech API. But of course, because in the Google Speech API, they don't use the Dysarthric dataset, so that their result is not good enough compared with our model, because our model only use the Dysarthric dataset. And the second stage result, we compare the recording result from the last day of the DSR. Last day means in the day 15th, we train the model and compare 3 kinds of the scenario. The first scenario is the personal DSR without the previous data. We don't use previous data here. And the second scenario is personal DSR with the previous data. And the third is the all data at once. As you can see, when we use the data from the previous one, it can be better if without data from the previous day. So as you can see in the second column, for example, we compare the mile CP01 in the daily without the previous data, we get the Syiah character error rate about the 5.21 to 21. When we use the previous data, it can reduce the Syiah to be the 3.79. So it can help if we use the previous data when we train the new model. But here, when we train the new model for the personal DSR, we use initial model. We don't train from the beginning, just use initial model to get the robust model for the personal DSR. And later, for the third stage here, we compare the result from the last day of DSR with or without synthesized speech. As I mentioned in the previous slide, I also performed the voice conversion, and here we compare how voice conversion can help when we use it in the training model. So you can see for the column 2 here, daily with the previous data, we got the result there. And then when we use the synthesis data, it can help, but not all of the Dysarthric level. For example, for the mild and moderate, it can help to reduce even a little bit, but it can help to reduce the CER, character error rate, when we incorporate the synthesized speed data with the previous data in Dysarthric dataset. So for the conclusion here, the first one is the TDNN and lifelong learning approach effectively improve Dysarthric speech recognition, especially for the severe CP case. And the key technique that we use here, by combining acoustic model with the data augmentation, it can enhance the system performance. And for the future work, the study that lay groundwork for the creating personalized model can help and expanding training data set for the Dysarthric. And for the future plan, we will focus on the different kind of the Dysarthric level, not only for the CP, but also for the CVA and LS. For the information, currently our application already can be downloaded in the Google Play Store, and then for the iPhone also available there. Yeah. Thank you. I give back to the moderator.
Questions?
Thanks for the talk. So you use lifelong learning, so I was curious what kind of the modification do you have with lifelong learning? Is just distribution adaptation, or is completely new classes which are used?
Okay, thank you, Professor Marcelo. So the idea behind lifelong learning is look like this thing. So in our experiment, we just want to simulate the lifelong learning state. So here, what we are doing is we split the data into several days. Why we call lifelong learning? Because, for example, for the people with the dysarthria disorder, we cannot record the data every day because they don't have the enough ability to speak for the several hours, something like that. So for example, in the day one, we only recorded 20 sentences. We provide the transcription for them, record the 20 sentence, and then in the next day, we record the next 20 sentence. And then we use this 20 sentence along with the another 20 sentence to train the new model. We call it a personalized model. And it also will be happen like that for the so on. This kind of process we mention as a lifelong learning. Yeah.
You don't have problem with the catastrophic forgetting. Lifelong learning comes always with the problem of what's called catastrophic forgetting. You forget what previous learner.
Yeah, that's why we designed this one to make sure that what forget from the previous one, we use the previous data to encounter this kind of the issue.
Retrain every time.
Yeah, retrain every time. But we don't train by not using the all of data, but only small data from that day. But the model we got from previous day, we use the transfer learning to get the weight from the previous day to train that model in the coming days. Yeah.
Okay, thanks.
Thank you. So from the title, this is quite interesting, but this is from Taiwanese Mandarin, right?
Yes.
So what about if, let's say, someone else want to try this approach to other language, right? What would be the challenges that need to be considered, let's say, if they are want to try this model?
Okay, thank you for the question. So currently in our experiment, we only have the Mandarin Taiwanese data set. But for those who want to try in another language, they can record the data, or they can get the data freely on the internet. I remember that they have the another data called as the Turbo data set. It's currently freely available for the English ones. Yeah, but this one is kind of the private data set because we recorded the data from the several hospital in Taiwan. Yeah, that's why it cannot really available if someone else want to do same experiment on this one. But I remember that some university in Taiwan also incorporate with our company, and they have the agreement and taking the data set to do the further experiment on this kind of the issue. Yeah.
Questions?
So, thank you. So I have a question regarding these decoder. Yeah, so you kind of artificially generated this Dysarthric speech by using standard language, and then you transformed it. Yeah. So this converter. So I think your model you're estimating can only as good as this converter is kind of, because how representative is this converter to all kinds of variation of Dysarthric speech you see around?
Okay, thank you very much for the question. So when we perform the voice conversion for the dysarthria, we cannot use all of the speakers. We only can use the small amount of the speaker. For example, in our experiment, we only use the 3 speaker from the dysarthria, and then the 3 speaker from the normal speaker. And then we just mapping normal speaker into the dysarthria speaker, choose one by one. Cannot use because the variation of the speaker will make the model will be unstable. That's why we choose a small amount of the speaker to train it one by one. Yeah, because here, when we perform the voice conversion, the goal is we only need the more data set, right? So the data set transcription without available in recording data. For example, if the user say new thing, say new sentence, so voice conversion can help to handle the new sentence say by the dysarthria people. Yeah.
No other questions?
Okay.
Great, then. Thank you.
you.
Okay, thank you very much.
Wow. Good job.
Our third speaker, Ayush.